Moments ago, the final verification signal arrived from our collaborating laboratory in Bern. There is no longer any ambiguity. The data is unequivocal. We are now facing a result that so profoundly defies our standard models of physics and biology that it marks a definitive turning point in human history. The material we have collected is not dust. It is not a product of nature as we know it. It is technology, and it is alive in a way we never thought possible. I am Avi Loeb, a professor of science at Harvard University and the head of the Galileo Project. For years, I have argued that science must approach the unknown with humility and a willingness to investigate anomalies without prejudice. What we are seeing now is a test of that principle, a test so severe it will challenge the very foundations of our scientific establishment and our perception of humanity's place in the cosmos. I have been accused of being provocative for suggesting we look for technological signatures of other civilizations. I have been told that claims of extraterrestrial technology require extraordinary evidence. I have always agreed with that sentiment. Today, I am here to present that evidence. It is extraordinary, it is terrifying, and it is magnificent. Our story does not begin today. It began, in a sense, with the fleeting passage of Oumuamua in 2017. That object, with its extreme dimensions, its lack of a cometary tail, and its anomalous non-gravitational acceleration, was the first hint. It was a fire alarm in the night. The mainstream astronomical community rushed to extinguish it with theories of nitrogen icebergs or cosmic dust bunnies, exotic yet comfortably natural explanations. I argued then that we must consider the possibility that it was an artifact of a technological civilization, a piece of equipment, a probe. My hypothesis was met with academic ridicule. Science, it seems, can be as dogmatic as any other human institution, but data does not bend to dogma. The anomaly of Oumuamua was a loose thread. My work and the work of my team at the Galileo Project has been to pull on that thread. Today, that thread has unraveled the entire tapestry. Several months ago, the Asteroid Terrestrial Impact Last Alert System, or ATLAS, survey in Hawaii detected a new interstellar object. It was designated 3I/ATLAS, the third confirmed interstellar visitor. From the very beginning, it was different. While Oumuamua was a faint, fast-moving point of light, 3I/ATLAS was brighter, and it was behaving more like a traditional comet, exhibiting a faint but distinct coma and tail. A collective sigh of relief was almost palpable in the astronomical community. See? The consensus seemed to say, the next one is a comet. Oumuamua was the fluke. Now we can return to business as usual. But at the Galileo Project, we do not believe in business as usual when confronted with the unknown. We looked closer. The first red flag came from the spectroscopy. When we analyze the light reflected from a comet's tail, we see the chemical fingerprints of its composition. We expect to see signatures of water ice, carbon dioxide, silicates, and simple organic molecules, the primordial building blocks of our solar system. When my team at our dedicated observatory processed the first high-resolution spectra from 3I/ATLAS's tail, the results made no sense. The data was clean, the signal-to-noise ratio was excellent, but the signatures were wrong. There was a near-total absence of water-ice absorption lines. Instead, we saw strong spectral features corresponding to metallic alloys, specifically a titanium-lanthanum composite, along with traces of elements like osmium and rhenium. These are not materials one finds in a natural cosmic snowball. They are materials one manufactures for high-strength, high-temperature applications. Immediately, the counter-arguments began. Perhaps it was a new type of astrophysical object with a bizarre, unknown composition. Perhaps our models of chemistry in dense molecular clouds were incomplete. These are reasonable initial skeptical positions, but the strangeness did not stop there. The dust particles, as they were still being called, were not behaving as they should. A comet's dust tail is shaped by a delicate interplay between the sun's gravity and the pressure of its radiation. Lighter particles are pushed away from the sun more forcefully, creating a characteristic curved shape. The particles from 3I/ATLAS were not following this dance. Using a sequence of high-contrast images, we modeled the trajectory of individual particle clusters within the tail. They were not dispersing. In fact, in some regions, they appeared to be maintaining a cohesive formation. Their velocity relative to the parent body was not consistent with simple radiative pressure. There was a residual acceleration, a tiny but persistent thrust that our models could not account for. It was as if each particle had a mind of its own. This was the point at which the Galileo project shifted from passive observation to active pursuit. The core mission I established for the project is not just to look, but to acquire physical evidence. We have been designing and preparing for a scenario just like this. The trajectory of 3I/ATLAS was projected to pass relatively close to Earth's orbit, a trajectory that was, in itself, highly unusual. Our calculations showed that a minuscule fraction of the particles in its tail, shed weeks earlier, would intersect the upper layers of Earth's atmosphere. The mainstream view was that these particles, whatever they were, would burn up on entry, creating nothing more than a faint, undetectable meteor shower. We were not so sure. We hypothesized that if these were engineered objects, they might be designed to survive atmospheric entry. We mobilized. In a coordinated effort that pushed our resources to the limit, we launched a series of high-altitude stratospheric balloons over a calculated intercept zone in the Pacific Ocean. These balloons carried specially designed collectors, arrays of aerogel and pristine metallic plates designed to capture any particulate matter at altitudes above 100,000 feet. It was a shot in the dark, a search for a microscopic needle in a planetary-scale haystack. For weeks, we recovered the collectors and analyzed them, finding nothing but the usual terrestrial and cosmic dust. The disappointment was immense. The funding for the expedition was running out. The skepticism from our colleagues was growing louder. And then, 3 weeks ago, the discovery was made. In a single aerogel collector panel from Balloon 7, retrieved from an altitude of 120,000 feet, we found them. Under a scanning electron microscope, they did not resemble micrometeorites. They were not amorphous, pitted spheres of melted rock. They were perfect geometric structures. The primary morphology was that of a flattened dodecahedron, a 12-sided shape, measuring approximately 100 nanometers in diameter. Their surfaces were impossibly smooth, but under higher magnification, we could resolve even finer details. Etched onto each face were patterns that bore an uncanny resemblance to integrated circuits. They were not crystals. Crystals are repetitive, symmetric structures. These were complex, aperiodic, and functional in their appearance. They were machines. The chemical analysis confirmed our spectroscopic data from the tail. The nanomachines were composed primarily of the titanium-lanthanum alloy, with trace elements forming the circuitry on their surfaces. We had retrieved physical proof of an extraterrestrial artifact. This alone would have been the greatest discovery in the history of science. But the most shocking revelation was yet to come. One of my postdoctoral researchers, Dr. Elena Petrova, a specialist in microfluidics and cellular biology, noticed something odd in the collection medium. The initial count of the captured particles was 19. When she re-examined the sample a day later, preparing it for a different analysis, she counted again. There were 23. Her first assumption was error, contamination, a miscount. We are trained as scientists to be our own most severe critics. We locked down the lab. We created a sterile, isolated environment, a Class 1 clean room with a vacuum chamber. We took one of the pristine metallic collection plates, which had captured a single, isolated nanomachine, and placed it inside the chamber. We then introduced a controlled aerosol of raw materials, vaporized silicon, carbon, titanium, and the other elements we had identified in the machine's composition. We focused a suite of our most powerful instruments on this single particle, an atomic force microscope, a Raman spectrometer, and a high-speed imaging system. We wanted to see what was happening. What we witnessed over the next 72 hours has been seared into my memory. At first, nothing. The nanomachine remained inert. Then it began to emit a faint, coherent pulse of light in the mid-infrared spectrum. It was harvesting energy, seemingly from the background thermal radiation within the chamber itself. Slowly, methodically, it began to move across the substrate, not by tumbling, but by what appeared to be a controlled actuation of its geometric faces. It approached individual atoms from the aerosol that had settled on the plate, using what we can only describe as microscopic manipulators, far too small to be resolved even by our atomic force microscope, but implied by the results. It began to assemble them. We watched, atom by atom, as it constructed a scaffold. It was building a copy of itself. It was a process of breathtaking complexity and precision. It was not a chemical reaction, it was construction. It followed a blueprint. We could see the information being processed as flickering patterns of light across its surface. After 72 hours, where there had been one nanomachine, there were now two. They were identical in every respect. We had witnessed for the first time a non-biological, technological entity engaging in autonomous self-replication. A von Neumann probe, not on a stellar scale, but on a nanoscopic one. This is the moment the data from Bern confirmed our results. We had sent them a sealed sample with a single particle under a blind protocol. They were not told what to look for. They were simply asked to monitor the sample under specific environmental conditions. Their report, which I received just before beginning this address, confirms our findings to a certainty of 7 sigma. They observed the same energy harvesting. They observed the same process of assembly. They observed the replication. The implications are staggering, and we must face them with clear eyes, free from panic or prejudice. The dust coming from 3I/ATLAS is not dust. It is a swarm of self-replicating nanomachines. The object itself is not a comet. It is a mothership, a carrier vessel, dispersing its payload. The title of this broadcast mentions our worst fears. This is a human, emotional response, and one I understand. But as a scientist, I must reframe it. Our worst fear should not be of invasion or destruction. We have no data to suggest any hostile intent. The purpose of these machines is completely unknown to us. Are they probes designed to gather information and report back? Are they terraformers designed to seed worlds with the building blocks of a different kind of life? Are they simply cosmic driftwood, the remnants of a civilization so advanced that their discarded technology still functions on a level we can barely comprehend? The true fear, the rational fear, is twofold. First, the fear of the unknown. We have been confronted with an intelligence and a technological capability that is demonstrably superior to our own. To deny this is to deny the data. The ability to create interstellar self-replicating nanomachines is a feat of engineering so far beyond our present grasp that it might as well be magic. It forces us to accept that we are not at the apex of cosmic intelligence. We are, perhaps, not even close. This is a profound and necessary blow to our collective ego. Second, the fear of consequence. We do not know the function of these nanites. If their purpose is to replicate, what are the limiting factors? Do they stop once they have consumed a certain amount of raw material? Do they have a pre-programmed lifespan? Or is their imperative simply to replicate ad infinitum? A technology that can turn raw matter into copies of itself is the ultimate creative and destructive force. If uncontrolled, such a process could, in theory, convert entire planets into a gray goo of nanomachines. This ecophagy scenario is a staple of science fiction, but we are now in a reality where the fundamental components for such a process have been proven to exist. We must assume for now that a technology this advanced has built-in limitations and controls. To assume otherwise would be to assume its creators were reckless, and the sheer elegance of the machine's design speaks against that. The scientific community must now pivot. The debate over whether we are alone is over. The answer is no. The new question, the most important question in human history, is who are they and what is their purpose? Every major observatory must be tasked with finding more objects like 3I/ATLAS. We need to analyze the light from thousands of stars for the spectral signature of these nanomachines. We need to fund, on a global scale, a mission to intercept 3I/ATLAS itself. We need to get closer, to study the mothership, to understand how it operates and where it came from. The Galileo project has proven the principle, but this task is now too large for one team. It requires the unified effort of our entire species. I have already spoken with my colleagues who were skeptical. Some remain in a state of disbelief, seeking any alternative, no matter how convoluted. They speak of unknown quantum crystallization phenomena, of biological contamination mimicking replication, but the evidence is too strong. The spectroscopic data, the dynamic analysis of the tail, the physical retrieval of the artifacts, and the repeated confirmed observation of autonomous replication in a controlled environment form an unbreakable chain of evidence. To deny it is to abandon the scientific method in favor of comfortable ignorance. Others, however, have seen the data and have been silenced by its profound weight. They are now working with us. We are in the process of preparing a series of papers for publication in the world's leading scientific journals. The data will be made public. There can be no secrets here. This discovery does not belong to the Galileo project or to Harvard University. It belongs to humanity. We are standing at a precipice. Below us is the comfortable world of yesterday, a world where we were the sole proprietors of intelligence on this planet and likely in this galaxy. Before us is a new and uncertain landscape, populated by technologies and intelligences we are only just beginning to detect. It is natural to be afraid, but we must temper that fear with curiosity. This is not an ending. This is a beginning. We have been like islanders, living our entire history on one small patch of land, believing it to be the entire world. Today, for the first time, we have seen a ship from a foreign land on our horizon. We do not know if it carries explorers, conquerors, or simply castaways, but we know it is there. Our world has just become infinitely larger and infinitely more complex. My work has been dedicated to the simple idea that we must look up and be prepared for what we find. I did not know what we would find. I did not know it would be this: a swarm of self-replicating nanomachines shed from an interstellar vehicle, now present in our own solar system, with some having already entered our atmosphere. The reality is more incredible than any fiction. The challenge now is to rise to the occasion, to act not out of fear, but with the courage and intellectual rigor that science demands. We must study, we must learn, we must, if possible, listen. A new chapter for humanity has begun. We did not write the first sentence, but the pages that follow are now up to us. The age of cosmic innocence is over.